Welcome to The Explainer. Today, we're looking at this incredible open source project that lets you model the entire human body from a totally steady heartbeat all the way to a catastrophic failure. And it's all done with just a few lines of code.
So, I want you to picture this. A patient is coding on a table. But wait, the patient is actually software. And the life-saving interventions, they're just commands you type into a terminal. I mean, that's exactly what this project does. It models the human body as a living, breathing, a living, running program.
Okay, so at its heart, this project is what's called a biomimetic system. And that's really just a fancy way of saying it's software that imitates life. Think about it. Each organ is its own little program, right? It's running all by itself, but it's also interconnected with everything else. And together, they create this digital human that we can actually learn from.
So that's the big question, right? How do you even begin to write a human in code? Well, it turns out it all starts with a foundation that's surprisingly elegant and pretty minimalist. You know, what's so remarkable here is the simplicity behind all this complexity. The entire system, it's built with pure Python, no external dependencies, just using its native tools to run all the organs at once. And get this, the simulation runs 10 times faster than real time. That means a crisis that would take minutes to play out in an ER, well, here it unfolds in just a matter of seconds.
Okay, so for a body to actually work, organs can't just be doing their own thing in a vacuum, right? They've got to talk to each other. And in this digital body, they don't have direct phone lines. Nope, all communication gets routed through a central network. So instead of making direct calls to each other, everything gets routed through 3 completely distinct communication buses. It's a great analogy. You can think of them as the body's internet, its postal service, and its broadcast radio. Each one serves a really different purpose, from delivering vital resources to zapping out urgent commands. So first up, we've got the bloodstream. And this thing acts like a big shared resource pool. It's not for direct messages, not at all. Instead, organs they reach in, they grab what they need to live, like oxygen and glucose, and then they dump their metabolic waste back in. It's basically the body's fundamental supply chain. Then you've got the nervous system. This is the body's high-speed, instant messaging network. It's zipping critical, time-sensitive signals all over the place. We're talking about things like the brainstem's direct command to the lungs to breathe, or that body-wide fight-or-flight alert that puts every single organ on high notice, instantly. And finally, there's the endocrine system. So if the nervous system is IM, this is more like a slow-wave radio broadcast. It's sending out hormones, like adrenaline or insulin, that create these gradual body-wide changes. It's what sets the overall mood and manages all the long-term stuff. All right, so with all those communication lines established, the system can finally boot up. It starts bringing organs online one by one, in a sequence that, and this is cool, actually mirrors early human development. And the sequence here is absolutely logical and vital. First, the communication buses go live. Then, the brainstem, think of it as the body's autopilot, kicks in. The heart starts its own beat, all on its own. But here's the crucial part. The lungs, they do nothing. They stay completely inactive until they get that breathe command from the brainstem. This sets up a critical dependency right from the very first moment of life. And this whole boot-up process isn't some mad dash to the finish line. Nope, there's a very carefully calibrated 50-millisecond delay between each organ firing up. It's this staggered start that makes sure the whole system stabilizes properly without just, overwhelming itself. Okay, so once all these individual organs are up and running, each one just following its own set of simple rules, well, something pretty amazing happens. A stable, lifelike state just emerges from all that complexity. It's pretty incredible. If you just leave it to its own devices, the digital human actually finds its own healthy balance. And this is where the real power of the model becomes so clear. Look at these vitals: heart rate, blood pressure, oxygen. They all settle right into normal, healthy ranges. And the key thing here is that nobody programmed it to do that. It's the natural, emergent outcome of all those separate systems just working together. But let's be honest. The real purpose of a simulation like this isn't just to model a healthy body. It's to model a crisis. And that is where this thing becomes an incredibly powerful training tool. The project's own documentation really highlights its most important feature, something called cascade failure. And it's exactly what it sounds like.
Just like in a real body, if one critical part fails, the whole system can unravel in a predictable and frankly terrifying chain reaction. Let's actually watch this happen. So when we run the kill brainstem command, the effect is immediate. Bang. Within a single second, the lungs just stop. 5 seconds later, oxygen levels are plummeting. And in just 15 to 20 seconds of simulation time, the heart, completely starved of oxygen, goes into cardiac arrest. The whole system just fails. And it's not just about pulling the plug on one organ. The system can run these pre-built medical scenarios to simulate specific emergencies. Take anaphylactic shock, for example. We can see the model perfectly reproduce the classic signs. The airway constricts, blood pressure just bottoms out, and the heart starts racing like crazy to compensate. It's a totally realistic crisis, right there on the screen. But here's the thing. You aren't helpless. You can actually intervene. The model has a whole pharmacology system with a library of drugs built in. You can administer epinephrine to treat that allergic reaction, or maybe give morphine for pain. But you've got to be careful. Every drug comes with realistic effects and, yeah, potentially dangerous side effects, like, say, suppressing the breathing rate. So let's zoom out for a second, because the crucial point here is that this project is about so much more than just biology. What we're really looking at is a blueprint, a pattern for modeling almost any complex, interconnected system you can possibly imagine. I mean, think about it. If you strip away all the medical terms, the core architecture is incredibly generic. What do you have? A set of independent agents, a few different ways for them to communicate, a list of key things to watch, and a set of challenges to throw at it. This pattern, it's universally applicable. And this, well, it leaves us with a really fascinating final thought. This exact same architecture, it could be adapted to model a financial market, or a global supply chain, or shoot, even the creative process of writing a novel. It's just a powerful template for understanding how simple rules can lead to incredibly complex behavior and, of course, catastrophic failure. So the question is, what would you build with it?